Okay, let's continue with the second part of this talk. The second part is more technical. So in this talk, we consider the following flow problem, which is xt equals minus r to the alpha times sigma 2 to the 1 over 2 times nu for alpha is greater than or equal to 2. So this is a generalization of what Li Shen Wang considered earlier. So what they did was one of the case for the non-convex case is xt equals minus r to the alpha times sigma 1, which is mean curvature, times nu for alpha greater than or equal to 2. So here we do it to scalar curvature. And notice that here we have scalar curvature to the 1 over 2 because then we can make this operator is homogeneous of degree 1. And more importantly, this is concave functional. So this is concave, which we will need this property to do estimate later. So what we proved is the following. We proved that if we start from a smooth, closed, two convex star-shaped hypersurface in Rn plus 1, so two convex means that the scalar curvature is positive and the mean curvature is positive. So we start from initial hypersurface like this. Then the flow 7 has a unique smooth star-shaped solution m sub t with positive scalar curvature for all time t greater than 0, which converges to the origin. And after proper rescaling, the rescaled hypersurface converges exponentially faster to a sphere centered at the origin. So, and alpha greater than or equal to 2 is optimal in the following sense, that we actually, when alpha less than 2, we actually constructed a counterexample. We find a uniformly convex initial hypersurface, because it's uniformly convex, so it's automatically star-shaped, and two convex, right? Because uniformly convex means that every principal curvature is greater than 0. And then we show that start from this type of initial surface, the max of the radiance over the minimum of the radiance goes to infinity in finite time, which means that in finite time this flow gonna pass the origin. So before it actually become a point, so it can't smoothly converges as a sphere. So okay, so we're gonna generally talk about the difficulty of proving the general curvature flow. So there are following difficulties for proving a nice result for general curvature flow. So first, there is a lack of monotonicity qualities. Usually, in order to study the asymptotic behavior of curvature flow, it's nice to have some monotonicity formulas. So such as very famously when Huisken studied mean convex mean curvature flow, he has some monotonicity qualities. And also for Gauss curvature flow, where Guang and Ni started, they found some, they used some monotonicity qualities as well, and that quality was first started by Ben Chao. And so even in the earlier in the work Li Shen Wang, where they prove xt equals minus r to the alpha times the Gauss curvature, which is sigma n, times smooth positive function f times mu. When they study the convergence of this flow, they also used some monotonicity qualities. So this is one difficulty to generalize this result to sigma k, right? Because we currently don't have a monotonicity qualities. So we can only do f equals constant essentially. So second, there is a lack of convexity estimate in the limit. So because if the hypersurface is convex, then in general, it's easier to get the curvature estimate. However, if we start from a non-convex hypersurface, we don't know in general for general fully nonlinear curvature flow if around the singularity it's gonna become convex. So ideally we would want it to become convex because it would simplify the analysis for the shape of singularity. However, in general, for general curvature flow, that's not true. But as we all know that it is true for mean curvature flow, and Ben-Andrews also proved that it is true for a large class of flow in dimension 2. But for n dimension in general, it's not known for sigma curvature flow and for large class of curvature flow. So finally, the difficulty is in doing the C2 estimate, which is a curvature estimate, because the admissible cone for general curvature flows can be very large. For example, if we consider a convex hypersurface, then the admissible cone is the convex cone. So which means that you started this flow in the cone that kappa 1, kappa 2, up until kappa n all positive. But in general, the cone is large. So for example, scalar curvature, right? We have some curvature is positive, have some curvature is negative. So that makes it harder in the sense that, for instance, right? So if we start the Gauss curvature, which is kappa 1, kappa 2, kappa 3 equals 1, right? Because it's a convex cone, if we assume that kappa 1 greater than or equal to kappa 2 or greater or equal to kappa 3, then find a lower bound for kappa 3 or find the upper bound for kappa 1, both can give us curvature estimate. In other words, it's the same thing, right? We either find the lower bound for the smallest curvature or find the upper bound for largest curvature. Then the length of the principal curvature vector is bounded. However, in gamma 2 cone, if we talk about kappa 1, kappa 2 plus kappa 1, kappa 3 plus kappa 2, kappa 3 equals 1. If we have a lower bound on kappa 3, doesn't give us upper bound on kappa 1, in fact. So and in order to bound the principal curvature, we actually need a bound on kappa 1. So we require an upper bound on the largest principal curvature. So this makes things more complicated. And in this paper, we introduce new techniques to obtain the curvature estimates. And we expect that these new techniques will be useful for other geometric problems. Okay, so next we're gonna talk about the ideas of the proof. So we follow the idea in decision 1, we consider the rescaled curvature flow. So it's easy to see that if we start from a star-shaped hypersurface, and if we assume that along the flow, every flow hypersurface is star-shaped as well, then the radial function r would satisfy equation 9. So like in order to study the behavior of this flow, or any flow, typically we needed to have a C0 estimate. In this case, the C0 estimate is bound on R, and C1 estimate, in which case it's bound on gradient R. C2 estimate, which is principal curvature estimate. But in order to get the principal curvature estimate, we usually need another estimate, which is we need an estimate on sigma 2. So because we pretty much need sigma 2 is bounded along the flow in order to get each principal curvature is bounded. That's what we're gonna do next. Okay, first we prove C0 estimate, and we let R be a positive 2 convex smooth solution to equation 9, and so equation 9 is here, and we show that R is bounded from above and below. So this part is actually very easy. We just consider the function R minimum of t, which is the point at each time that R minimum of t is the smallest radiance of mt, and then we can derive ODE, and this ODE tells us that the minimum radiance actually increasing along the flow. So then we have a lower bound for R, and similarly we can have the upper bound, in which case we just consider R max of t equals max R dot t, right? So then similarly we have dr max dt less than or equal to 0, then we have upper bound. So this is a C0 estimate. Okay, next we're going to consider the C1 estimate. Recall that our function u is the support function x dot nu, right? And nu actually depends on the gradient r. So in order to get a gradient estimate, we only need to bound the support function. And the upper bound for this support function is obvious because it's easy to see that u is always less than or equal to the length of x, which is our r, right? Because in our first lemma, we already showed that r is bounded from above. So u is obviously bounded from above. So what we need to do is to show that u is bounded from below. Okay, so we can see that since u, if we write it as a function of r, equals r squared over square root of r squared plus gradient r squared. So we see that in order to obtain a C1 estimate, which we only need to show that u is bounded from below, so we will consider the following auxiliary function, p, which is lambda over s minus log u. Okay, so the reason we consider this auxiliary function, so roughly speaking, right, in order to get a C1 estimate, auxiliary function usually including terms from C0, right? In this case, it's r squared, right? So it's in order to get C1 estimate, so our auxiliary function is a function of r and gradient r, right? So basically, when we want to do estimate, it's always follow this rule, right? In order to get C2 estimate, our auxiliary function would be R gradient R, and the gradient would contains R gradient R and the gradient square R. Pretty much it's like this. So anyway, we find this auxiliary function, and then we apply the maximum principle. We can show that at the interior maximum point of P, we have U square greater than S over Q, because we already have a bound on R square, so we know that this implies that U square is greater than some constant C, right? Because S is bounded from below. From our first lemma, we already know that. And this would lead to a conclusion, right? So because at the maximum point of P, U square is bounded below, so we know that P is always P is bounded above, so then U is always bounded below. Okay. So next, we're going to prove our main theorem, which is our C2 estimate. Okay, before this proof, let's talk about what we already know, right? So what we already know is we know that R is bounded from above and below, and U is bounded from above and below. And then there's another lemma, which says that sigma 2 is bounded from above and below, which I didn't mention for because of time, because the estimate of sigma 2 is very similar to this C2 estimate, but the process is much simpler. However, the idea is very similar. So I didn't talk about it, but in our mind, we know that, okay, now our R and U and sigma 2 both bounded from above and below by positive number. Okay, so next we want to show that under the normalized flow A, flow 8, there exists a constant C depending on the initial surface M naught, R, N is the dimension, U and sigma 2, such that the principal curvature, or the absolute value of principal curvature, is bounded. So that's what we're gonna prove. Okay, in this proof, we always assume that kappa 1 greater than or equal to kappa 2, and greater than or equal to up to kappa n. So we always assume this. So first, we note that because h squared, where h is the mean curvature, minus a squared equals 2 times sigma 2, which is greater than 0. So in order to bound a squared, we only need to bound mean curvature h. Therefore, we consider the auxiliary function q equals log h minus log u minus a. We only need to show that h is bounded from above, then we're done, right? Okay, here a equals the 1/2 of the minimum value of u. As we said, we already know that u is bounded from below by a constant, by a positive number, so this is okay. Okay, then we assume that Q achieves its maximum at an interior point, right? Because if Q achieves its maximum point, achieves its maximum at the boundary when t equals 0, then we would be done, right? So we assume it achieves its maximum at an interior point. Then at this point, we have LQ, which is QT minus R to the alpha times FIG, QIG is greater than or equal to 0. This QIG is actually gradient I gradient j of q, and Fij is the partial sigma 2 1 over 2 partial Hij, where Hij is the second fundamental form. Okay, so then we just compute this whole thing directly, and this is the right-hand side. The right-hand side looks very long, right? Very complicated, but we can easily see that okay, this term is bounded because R is bounded, F, which is sigma 2 to the 1 over 2, is bounded, U is bounded, and gradient R is bounded. So H we don't know, but here is divided by H, so this whole term is bounded, under control. And similarly, this term is under control, and this term under control, this term under control, and this term is under control. So there's only one, two, this term is under control because minus H over H, which is minus 1. So it's only 1, 2, 3, 4 terms are not controlled. So we can simplify this equation, and this equation gives us following, right? So this term comes from we combine this plus R to the alpha H sum Fi kappa I squared with the last term, right? So here, yeah, I forgot to say that this equals Fi times delta Ij when Hij is diagonalized kappa I delta Ij. Okay, so that's our notation. Okay, so then we essentially want to analyze inequality 11, right? So we can see that this term, right, despite we don't know exactly what this term is, but as we said at the very beginning, sigma 2 1 over 2 is a concave functional, which equivalent to say that actually this term is less than 0. Okay, so what we really don't know essentially is just this term. Like we have no idea if it's positive, negative, or how big it is.